Nanostructures come in different shapes and sizes and are classified based on their dimensions. We have zero-dimensional or 0D nanostructures like nanoparticles, two-dimensional or 2D nanostructures like nanosheets, and three-dimensional or 3D nanostructures like nanospheres. Today we will focus on one-dimensional or 1D nanostructures. 1D nanostructures such as nanowires and quantum wires have one dimension in the nanometer scale, while the other two dimensions are considerably larger. Imagine a really thin wire or a long, skinny rod. That's what 1D nanostructures look like at a nanoscale. These tiny structures are of significant importance in the realm of nanotechnology. Their unique size and shape confer them with distinct properties that can't be seen in their bulk counterparts. For instance, 1D nanostructures can conduct electricity and heat in a single direction, which can be very useful in electronics and thermoelectric applications. Moreover, the small size of these structures allows for a high surface-to-volume ratio. This means that a large portion of the atoms are on the surface of the structure, which can significantly affect the chemical reactivity and physical properties of these materials. This feature makes them an ideal choice for applications such as sensors, where surface interactions are crucial. Furthermore, the quantum confinement effect in 1D nanostructures can lead to novel electronic and optical properties. This effect occurs when the dimensions of the structure are so small that they confine the motion of electrons, altering their energy levels and leading to unique phenomena such as quantum tunneling and quantum superposition. So, in essence, one-dimensional nanostructures are at the heart of many technological advancements we see today. Now, let's explore the world of nanowires and quantum wires. These one-dimensional nanostructures have fascinating properties that stem from their size, shape, and quantum confinement. Let's start with their electrical properties. Nanowires, due to their small diameter, exhibit high conductivity and low resistance. This is because they have only a few conduction paths, minimizing scattering and enhancing electron mobility. Quantum wires, on the other hand, are an extreme version of nanowires where quantum confinement plays a significant role. This confinement leads to quantization of energy levels, which in turn affects their conductivity. Moving on to optical properties, both nanowires and quantum wires display unique absorption and photoluminescence characteristics. Their small size and high surface-to-volume ratio lead to enhanced light absorption and emission. This makes them incredibly useful in optoelectronics, where they can be used to create more efficient light-emitting diodes and solar cells. Mechanically, nanowires are surprisingly strong. Despite their tiny size, they exhibit high tensile strength and elasticity. This is due to their crystalline structure and the absence of structural defects. These properties make them ideal for use in various material science applications, including in the manufacturing of durable and flexible electronics. Finally, let's talk about thermal properties. Nanowires have low thermal conductivity, again thanks to their small size and high surface-to-volume ratio. This property is particularly important in electronics, where managing heat is a critical issue. With nanowires, electronic devices can be made smaller and more efficient without worrying about overheating. In summary, the basic properties of nanowires and quantum wires, their electrical, optical, mechanical, and thermal characteristics are significantly influenced by their one-dimensional structure and quantum confinement. These unique properties make nanowires and quantum wires indispensable for a myriad of applications. From electronics to optoelectronics, material science to thermal management, these tiny structures have a big impact. Creating these one-dimensional nanostructures is a feat of engineering in itself. So, how is it done? There are two primary approaches, bottom-up and top-down. In the bottom-up approach, we build the nanostructures atom by atom or molecule by molecule. It's like building a Lego tower by stacking one block on top of another. Techniques such as chemical vapor deposition, template-assisted growth, and molecular beam epitaxy fall under this category. Chemical vapor deposition, or CVD, involves reacting gases to produce solid materials on a substrate. It's a popular method due to its ability to produce high-quality, high-performance materials. Template-assisted growth, on the other hand, uses a pre-existing pattern as a guide for nanostructure formation. It's like using a stencil to draw a picture. And then there's molecular beam epitaxy, a method that allows for precise control over the thickness and composition of the nanostructures. On the flip side, we have the top-down approach. This is like carving a sculpture out of a block of marble. We start with a larger piece of material and then remove parts of it to create the desired nanostructure. Techniques such as lithography, etching, and electrospinning fall under this category. Lithography uses light or electrons to pattern a photosensitive material, which is then developed to reveal the nanostructure. Etching, as the name suggests, involves selectively removing material to create the nanostructure. And electrospinning uses an electric field to create fine fibers from a liquid. Each of these techniques has its own advantages and limitations. Bottom-up methods allow for atomic-level control and can produce complex structures, but they often require high temperatures and can be time-consuming. Top-down methods, meanwhile, are typically faster and can produce large quantities of nanostructures, but they tend to have less control at the atomic level. These techniques have evolved over time, enabling us to fabricate better, more efficient, one-dimensional nanostructures. Quantum wires, in particular, hold a world of possibilities. As we dive deeper into the realm of these one-dimensional nanostructures, we encounter the intriguing phenomenon of quantum confinement. This effect is a direct result of the tiny dimensions of quantum wires, and it fundamentally alters the way electrons behave within these structures. It's like confining a bird to a cage. The bird, or in our case, the electron, can only move in certain ways, thus changing its energy levels and the overall electronic and optical properties of the material. To better understand quantum wires, several theoretical models have been proposed. One of the most notable is the infinite potential well model. This model, although simplified, provides valuable insights into the electron density states within a quantum wire. It visualizes the wire as a well with infinite walls, where an electron is confined. The electron, much like a wave, has certain allowed states within this well, giving rise to distinct energy levels. But with all its promising potential, fabricating quantum wires is no easy task. The challenge lies in precisely controlling their dimensions on the nanoscale, while maintaining their structural and chemical purity. Several strategies are being explored to overcome these hurdles. Bottom-up approaches like chemical vapor deposition and template-assisted growth allow for the assembly of quantum wires atom by atom, offering a high degree of control over their size and composition. On the other hand, top-down approaches such as lithography and etching start with a bulk material and carve out the desired nanostructure. Both methods have their own advantages and limitations, and the choice often depends on the specific requirements of the application. Quantum wires, with their unique properties, are a promising avenue for future technology. As we continue to unravel their secrets, we inch closer to a future where the line between science fiction and reality blurs, a future powered by the marvels of nanotechnology. So, where exactly do we use these one-dimensional nanostructures? Let's dive right into the fascinating world of their applications. In electronics, nanowires and quantum wires are making waves. They're enhancing the performance of transistors and integrated circuits, allowing for even greater miniaturization. Think of the possibilities this opens up: smaller devices with more power and efficiency. But it's not just about making things smaller. These nanostructures also have a big role to play in sensors. Whether it's chemical, biological, or environmental sensing, nanowires and quantum wires offer high sensitivity and selectivity. Imagine a world where we can detect toxins in the air or disease biomarkers with a tiny, unobtrusive device. Switching gears to energy, nanowires are revolutionizing photovoltaics. They're being used in solar cells to enhance light absorption and conversion efficiency. This could lead to more effective solar panels, harnessing the sun's energy in a more efficient way. And let's not forget about batteries and supercapacitors. Nanowires are improving energy storage capacities and charge-discharge rates, making our devices last longer and charge faster. In the realm of photonics and optoelectronics, nanowires and quantum wires are enhancing the performance of LEDs and lasers. This means brighter, more efficient lighting and displays. They're also being used in photodetectors for applications in imaging, security, and communication technologies. Finally, in the medical and healthcare sector, nanowires are transforming drug delivery systems. They allow for targeted delivery and controlled release, making treatments more effective and reducing side effects. Nanowires are also being used to detect biomolecules for diagnostics and monitoring, paving the way for early disease detection and personalized medicine. These applications only scratch the surface of what's possible with nanowires and quantum wires. The potential is vast, and we're only just beginning to tap into it. From electronics to healthcare, these tiny structures are making a big impact. And as our understanding of their properties grows, who knows what other applications we'll discover. These nanostructures have some intriguing advanced properties. Let's begin with quantum mechanical effects. In the world of nanowires and quantum wires, we're dealing with dimensions that are so small, they're at the quantum level. This means we need to consider phenomena like quantum confinement, which occurs when electrons are confined to a space that is comparable in size to their wavelength. This can lead to observable quantum effects such as the formation of discrete quantum dots, or the manifestation of ballistic transport, where electrons can travel long distances without scattering. Even single electron tunneling, a phenomenon where an electron can tunnel through a barrier it wouldn't normally be able to cross, becomes a tangible reality in these structures. Moving on to surface and interface phenomena, the small size of these 1D nanostructures means they have a high surface-to-volume ratio. This greatly impacts their reactivity and catalytic properties as more atoms are exposed on the surface. It also affects surface plasmon resonance, a phenomenon where the conduction electrons on the surface of the nanowire resonate with the light's electric field, leading to strong absorption and scattering of light. Lastly, we come to band gap engineering. The band gap is a crucial property of semiconductors, dictating their electrical and optical characteristics. With 1D nanostructures, we can manipulate the size and shape to tune these properties. This is achieved through quantum confinement effects, where reducing the size of the nanostructure can increase the band gap, altering the material's conductive and optical properties. In essence, the advanced properties of 1D nanostructures stem from their unique quantum mechanical behavior and their high surface-to-volume ratio. These traits allow us to engineer the properties of the nanostructures to fit specific applications from optoelectronics to quantum computing. These advanced properties open up even more applications and possibilities for 1D nanostructures. Quantum wires also have some particularly fascinating advanced concepts. Let's delve into a few, starting with the electronic band structure. In the realm of quantum wires, changes in the electronic band structure are a big deal. They're the result of quantum confinement effects, which significantly alter the energy levels of electrons. This is a game changer for quantum computing, where the manipulation of these energy levels could be harnessed to create powerful quantum bits, or qubits. Next up is spintronics, a mind-bending field that leverages not only the charge of electrons but also their spin. Imagine a world where quantum wires are the highways for spin-based electronics, fostering spin transport and manipulation within these tiny structures. The result? A whole new dimension of electronic devices that are potentially faster, smaller, and more energy efficient than anything we've seen before. But wait, there's more. Let's talk about topological insulators. These are a new class of quantum wires that have been stirring up quite the excitement in the scientific community. Topological insulators are unique because they behave as insulators in their interior, but conduct electricity on their surface. This dichotomy is due to their unique edge states, which are immune to scattering and can carry current without resistance. This makes them incredibly promising for quantum computing. We've just scratched the surface of these advanced concepts, but it's clear that they're nothing short of revolutionary. The electronic band structure, spintronics, and topological insulators are pushing the boundaries of what we thought was possible with quantum wires. They're giving us a glimpse into a future where electronics and computing are no longer constrained by the physical limits of traditional materials. They're showing us that in the world of quantum wires, the possibilities are as vast as the universe itself. These advanced concepts of quantum wires could revolutionize the future of electronics and computing. Let's take a look at some of the more complex applications of 1D nanostructures. Quantum wires are at the forefront of quantum computing. They serve as the building blocks for qubits, the fundamental units of quantum information. This opens up a world of possibilities, where we can process information at unprecedented speeds and volumes. On another front, nanowires are making their mark in the realm of nanophotonic circuits. These circuits, which use light instead of electricity to communicate, offer ultra-fast data processing and communication capabilities. But the applications of 1D nanostructures don't stop there. Nanowire-based metamaterials are being developed, exhibiting novel electromagnetic properties. These materials are not found naturally and can be engineered to have properties such as negative refractive index. As we can see, the potential applications for 1D nanostructures are vast and truly exciting.